Hi everyone, this is Dr. G. Ravindranath Reddy, working as Assistant Professor in MLR Institute of Technology, Hyderabad. So we are discussing numerical methods and integral transform course. In that course, we are at the numerical solution of ordinary differential equations. So now we have different methods to find out the numerical solution of ordinary. So in this we are discussing Euler's method here. So in this video, we are going to discuss the numerical solution of ordinary differential equation by using Euler's method with some examples here. In the previous video, we have seen how to solve the differential equation numerical solution of ordinary differential equations by using Taylor's method. And in this, we are using Euler's method to solve the solution, to get the solution for the ordinary differential equations. So now, first we will see formula to how to derive the Euler's method formula. So now, this is also a very simple method, but whatever the solution we get, that solution is less accurate. So this is not a more accurate solution we get by using this Euler's method. So hence it has a limited applications here. So now let us consider the differential equation. So all these methods, whatever the methods we are going to discuss, we are taking only the first order differential equations. Now take the first order differential equation. This is our standard form of first order. Dy by dx is equal to f of x comma y with the initial condition. For this method also, we want initial condition. For all the numerical methods along with the differential equation, we want initial condition. This is our standard form of initial condition. Y of x naught is equal to y naught. Let it be equation 2. Now consider the first two terms of Taylor's expansion when x is equal to x naught. So in the previous video, we have seen the Taylor series expansion. Now by using this Taylor series expansion, we are going to derive the formula for Euler's. So now I have taken first two terms here. Y of x naught plus x minus x naught by 1 factorial into y dash x naught. So this is our first two terms of the Taylor series expansion when x is equal to x naught. Now from equation 1, I want to get y dash of x naught value here. So already in the previous we have seen if you want to get y dash of x naught value, so this is we got y dash is equal to f of x comma y. Now from this I want to get y dash of x naught value. So just replace x with x naught here in the function, and suppose if you have y, replace that y value with y naught. So this is our y dash of x naught is equal to x naught f of x naught comma y of x naught. This can be written as x naught is x naught comma y naught is that can be written as y of x naught. All these things we have seen in the previous video whenever we are discussing about Taylor's. So y of x naught, we can represent this as y naught value. So now substitute this y dash of x naught value in this equation. In the third equation we get y of x is equal to y of x naught plus x minus x naught into, so this y dash of x naught we can replace with f of x naught comma y naught here. So now this can be written as when x is equal to x1 and y of x1 is equal to y naught, this is our value. So just replacing that in point where we have to find out that numerical solution for the given differential equation. So I am taking that first x value as x is equal to x1, we get y of x1 is equal to, whenever we want to get that y of x1 value, we have to consider x naught and y naught as the initial condition. That's why we have taken this entire formula in terms of x naught and y naught here. So y of x naught, we can take it as y naught plus this one x1 minus x naught. So we can consider this as h value, h into f of x naught comma y naught. So this is the standard formula we will use for the Euler's in order to get y1 value here. So y1 is equal to y naught plus h into f of x naught comma y naught. So this is the formula we will use to find out y1 value here. And similarly, so whenever we want to find out that y2 value, so replace, so already in the Taylor's we have said that whenever we want to find out that y2 value, we have to consider x1 and y1 as the initial values. So wherever we are having x0, replace that x0 with x1. Wherever we are having y0, replace that y0 with y1 in the previous formula. So y2 is equal to y0. We have to replace that y0 with y1. So we will get y1 plus h into h is common throughout the problem. So replace x0 with x1 and y0 with y1. This is our standard formula to find out y2. So that is the thing here. So in general, so like this, whenever we want to find out x3, y value at x3, y value at x4, y value at x5. So in general, we can consider this standard formula. So proceeding like this, whenever we are having n number of values here, then this can be written as y suffix n plus 1 is equal to yn plus h into f of xn comma yn. So where n takes the values from 0, 1, 2, 3 and so on. So when we take n is equal to 0, you will get this formula. When we take n is equal to 1, we will get this formula. And similarly, when we take n is equal to 2, then we will get another formula to find out the y3 value. And similarly, when we take n is equal to 3, we will get formula to find out y4. That can be written as y3 plus h into f of x3 comma y3. So like this, we can use the standard formula to find out solution for the given differential equation using Euler's method. So whatever the numerical solution we get by using Euler's method, that is not accurate value. So this we can call it as a Euler's formula. Now let us take one example how to use this Euler's formula to find out the solution. So using Euler's method, solve for x is equal to 2. So at x is equal to 2, we have to solve this differential equation. So this is our differential equation and this is our initial condition. And by taking the step size, or we can take it as step length. Step length is represented with h. So one case he has given us, take h is equal to 0.5 and find out the values, whatever the values we get up to x is equal to 2. And the second case is take x is equal to 0.25, then whatever the values of x we get by taking this length h is equal to 0.25, at that values of x we have to find out the solution for this differential equation. Now let us take the case 1. So before that, first we will take the dy by dx differential equation with the initial condition and we will get x0 and y0 values here. So here, by comparing this with the standard form dy by dx is equal to f of x comma y, this is our standard form of differential equation. Now compare these two, the standard form with this given differential equation, we got f of x comma y is equal to 3x square plus 1, and compare the standard initial condition with the standard form. So in place of x0 here we are having 1, in place of y0 here we are having 2. So x0 is equal to 1 and y0 is equal to 2. So these are the primary things we want from the given differential equation along with the condition. Now Euler's algorithm, that is Euler's formula. So just now we have seen the general form of Euler's method. Take that general form and we said that n takes the values of n equal to 0, 1, 2, 3 in order to get our required values here. Now take h is equal to 0.5. I am at the first case, taking h is equal to 0.5. So now by taking h is equal to 0.5, we have to construct, if you construct the table, then we can get what are the values of x we get. So our in the problem he is asked to find out the solution at x is equal to 2. But here he has mentioned one condition, that h value, so the difference between the value of x and the value of x0, the difference must be 0.5. So here x0 is equal to, we got x0 is equal to 1 and this x value has given as 2. Suppose if we take the difference between these two, the difference must be equal to this h value here. But the difference between x0 and h value is not is equal to 0.5. So we have to divide 1 comma to this interval into a sub-intervals whose length is equal to 0.5. That is the problem. You have to remember this point here. So now let us take the table here. So initial value, we will represent that initial value with x0. In the problem he has given x0 is equal to 1. And x1 value he has given as x0 plus h, and x2 value he has given as add h value to its previous. You will get 2. So that means we are going to find out y0 value, y1 value and y2 value here. Now n is equal to, take n is equal to 0 in equation 1. You will get y0 is equal to, y1 is equal to y0 plus h into f of x0 comma y0. Substitute these values y0 2 and h value is 0.5 and calculate this f of x0 comma y0. x0 is equal to 1 and y0 is equal to 2. Simplify this, you will get y1 is equal to, that is at x is equal to 1.5, we got y value is equal to 4. And similarly you take the next x here, n is equal to 2 and get the y2 value, that is y2 is nothing but finding the value of y at x is equal to 2. So you substitute this in this formula, we will get y2 is equal to 4 plus this. If you simplify this, you will get y of 2 is equal to 7.875. So like this we have to consider h value, we have to keep that h value in the mind, and we have to divide x0 and h value into a sub intervals. In order to get that difference between these h values must be equal to the h value. So now you take h is equal to 0.25. So once again you draw the table here. Take h, y. So x0, that x0 is fixed throughout the problem. x0 is equal to 1 and y0 he has given that y0 value is equal to 2. Now here we have to find out the value of y at x is equal to 2. So our x value is equal to 2. Now once if you find out the difference between this x0 and x value, that should be equal to the h value what he has given in the problem. But here the difference between x0 and h is x0 and x is equal to 1, which is not equal to this h value here. Now what we have to do is we have to divide this interval 1 comma 2 into a sub intervals whose step length is equal to 0.25. Now according to this condition we have to construct the table here. Now the first, after x0 value we will represent that x value as x1. In order to get this x0 to x1 value, just add this h value its previous value. Our previous value is x0. So previous value, and we have to add that h value here. So previous value is 1. If we add 0.25 to this one, you will get 1.25. That is our x1 value. And similarly x2 is equal to, add that h value to its previous. What is our previous value? 1.25. So if you add that 0.25 to this 1.25, you will get 1.5. And similarly x3. So previous value is 1.5. If you add 0.25 to this, you will get 1.75. That is x3. And next go for x4. So x4 is equal to x3 plus h value. 1.75 plus 0.25, you will get 2. So until we get the 2 value as x value, we have to proceed this table here. Now our question is finding value of y1 at x is equal to x1, that is 1.25, and finding the value of y2 at x is equal to x2, that is 1.5, and y3 at x is equal to 1.75, and y4 at x is equal to 2. So since in the problem he has mentioned that h value, according to that h value we have to take the values of x. Suppose if the h value is not mentioned in the problem, then directly we can take x is equal to 2. We will get, by taking x naught is equal to 1, you will get h value is equal to 1. So since in the problem particularly he has mentioned the values of h, according to that h value we have to take the subinterval between x naught and x value given in the problem. So this is one interval, x naught and x1 is one interval whose length is 0.25, and x1 and x2 is another interval whose length is 0.25, and x2 and x3 is another interval whose length is 0.25. So these are the subintervals here. So according to this h condition, according to h value, we have to divide that interval into a subintervals. The length of that subintervals must be equal to the value of h. Now the question is finding y1, y2, y3 and y4. Now use the same procedure of Euler's which we followed in the case 1. So y1 value, y1 is equal to y0 plus h into h is, in the second case we have to take the h value as 0.25. So next f of x0 comma y0, and next y2 is equal to, so whenever we want to find out that y2, we have to consider its previous values. Our previous values are x1 and y1. So replace y0 with y1 plus h into f of x1 comma y1. This is the formula we will use to find out y2. And similarly y3 is equal to, so whenever we want to find out that y3, its previous values, our previous values of y3 is y2 and x2. So replace y1 with y2 plus h into f of x2 comma y2. And next, if you want to find out y4, its previous values we have to consider as the initial conditions. So y3 and x3 becomes the initial values to find out y4. So you will get y4 is equal to y3 plus h into f of x3 comma y3. Use these formulas to find out y1, y2, y3, y4. So already we have discussed how to find out y1 and y2 in the previous slide. Now use this to find out y3 and y4. Simplify this, you will get our required values here. So the important point what I want to say in this problem is, even though he has given asked to find out the solution at x is equal to 2, but according to this condition he has given h value. So even though if you want to find out x is equal to 2, solution of numerical solution of given differential equation at x is equal to 2, we have to concentrate on the h value here. If the h value is given in the problem, according to that h value, we have to divide that interval into a subintervals whose length of that subinterval must coincide with h. That is the important thing we have to remember here. So in this we have discussed how to apply these numerical methods, that is Euler's method, to find out the numerical solution of ordinary differential equation. So we said that whatever the solution we get by using this Euler's method, this is not more accurate value here. So in order to get more accurate value, Euler's formula is modified. That method we can call it as a modified Euler's method. So we'll discuss this modified Euler's method to find out the numerical solution of ordinary differential equations in the next video. Thank you all.